Uh, First, let me thank the organizers for giving me this opportunity to present my work. So what I'm going to talk today is on, again, the effect of disorder, but now I am introducing disorder in a Hamiltonian which has a permutation symmetry. This work is done along with Manju and Arul from IIT Madras and has been published in these two references. So before I actually go to the main work, slight motivation. So transmons, these are good candidates for qubits and which can be used in quantum computing. What has been found is these transmons are superconducting qubits, these are nonlinear oscillators. So what has been found is that if you randomize the energies of these qubits, then these become more stable qubits and randomized in the sense that you introduce some randomness or disorder in the qubit energies, and that helps to stabilize the qubit, but with a caveat that sometimes the disorder and the parameters of the Hamiltonian are so that the system is dangerously close to the face of uncontrollable chaotic fluctuations, and then using such qubits for the intended application becomes challenging. Now this is one place where there is an interplay between chaos and disorder, and the rest of the talk is also on that, how disorder brings in chaos in the system and what are the properties or how does various observables behave because of the disorder.
So what is dangerously? Because there is a meaning of dangerously.
Dangerously in the sense that it just takes you to the chaotic phase and they don't behave the way they. No, nothing. So yeah, so the model that I'm going to focus on is an all-to-all interacting qubit Hamiltonian, which has a classic. So in the disorder-free case, the Hamiltonian. So it's also periodically kicked. So there is an all-to-all interacting in one direction, and the system is periodically kicked in the transverse direction. In the disorder-free limit, this particular Hamiltonian has a classical limit, and it shows, and as I show in details, that there is, for certain parameters, the system dynamics is regular, and for certain other parameters, the system dynamics becomes chaotic. This has been well studied. It's the famous quantum kick top. And what I am going to do is to introduce disorder in this all-to-all interacting system, and then study various properties or various operators and study and show what happens. Okay, so that's the main essence of the talk today. So what is chaos? Chaos is high sensitivity to the initial conditions, and it essentially arises because some of the reasons for bringing in chaos are, for example, non-integrability or non-linearity. And when the system is chaotic, you can explain the dynamics using random matrix theory. And popular examples are weather systems. So if there is a slight change in the pressure or temperature of the system from the expected values, the long time behavior of the weather system completely changes. So now this is the Hamiltonian that I'm going to focus, which is you have some n spin half qubits, and these qubits are interacting, all the qubits are interacting with each other with some constant parameter. K is called the chaos parameter, and there is this transverse kicking with some strength P, which I am going to fix in the later on discussion, and these are kicked periodically at an interval tau. This Hamiltonian, because of the particular all-to-all interaction terms, can be written as using these collective spin operators. So if you define your Jx to be summation over sigma ix by 2 over all qubits, then we can easily convert this Hamiltonian in terms of these collective operators Jx and Jy, and it can be seen that the total angular momentum J square will commute with the Hamiltonian, and as a result it will be a constant of motion. It respects permutation symmetry because no spin is special. Every spin is interacting with every other spin with same strength. So you can just interchange spins, there is no, so permutation symmetry is present. And so as I said that the total angular momentum is a constant of motion. So therefore if you start with some j value, the system will continue to remain in that total angular momentum value. So that's the thing. So in the case of disorder free system, let me just talk about the disorder free case. Yes.
The kicking does not break the symmetry, rotation symmetry?
The permutation symmetry will still be there. Yes. And so you have this, my initial state in the entire dynamics would be this spin coherent state where each qubit is along the direction theta and phi. So they are all parallel to each other in this theta phi in a Bloch sphere. And so if you start from such a spin coherent state, one can see that your angular momentum quantum number j is equal to n by 2. Therefore, your j square is always some constant in this dynamics, and the Hilbert space for this particular system instead of 2 to the power n would be n plus 1, because j can take values from minus n by 2 to, so the z component can take values, for example, from minus n by 2 to n by 2. So therefore, the Hilbert space to which the dynamics is restricted is n plus 1 instead of 2 to the power n, and what we see is, so what people have studied extensively is the particular limit where j is infinity, that is you have many number of spins, and one can draw the phase space diagram for different chaos parameters k, and what is seen is that, for example, if k is 1, then the trajectory is regular. Again, I am talking about the disorder free Hamiltonian, and what it means is that suppose you start from some theta phi and evolve the system, then it repeats its trajectory or it is regular. On the other hand, if I increase k to a very large value, then if I start from some any theta phi here, it just goes to, it explores the entire phase space. So there is this change in the nature of dynamics from predominantly regular for small k values to chaotic in large k limit. So this is the classical dynamics, and one can similarly do the quantum dynamics with finite n, where now you have a periodic system. So you apply the Floquet theory, Floquet unitary operator, and so you start from some spin coherent state, apply the unitary operator n times to find out the state at nth time step, and so once you know psi n, you can always calculate various quantities. So for example, one that I am showing here is this linear entropy, which is reduced if rho q is the reduced density matrix of q qubits, then the linear entropy is just defined as 1 minus trace of rho q square. And if I plot this saturation value of rho q, the saturation value may be clear in the disorder case when if I forgot to put the variation of linear entropy as a function of n. But if you take a long time average of the linear entropy and plot it in the theta phi plane, what we see is structures like this, which are very similar to the classical phase space structure that I showed you in the previous slide. For example, you had these regular structures around these points, pi by 2, pi by 2, and when you go to the mixed phase corresponding to the classical phase, you had these special regular orbits or periodic orbits at these points, where now we see the linear entropy to be small. And chaotic phase has some structures, but they don't have any connection with the classical limit. So now let's go to the main thing, which is introduce disorder in the system.
Sorry, what is the signature for chaotic?
No, so I am not connecting the only thing that we see is that the entropy increases, the magnitude of the entropy increases. So now let me introduce disorder in the Hamiltonian. So the way I am introducing the disorder is in this coupling term, all to all spin coupling term, and I choose this epsilon LL prime from some normal distribution with 0 mean and a variance W. Yes.
So basically, all 12 can be mapped to a large scheme, right?
Yes. That's what your the kick top is. Yeah.
So for the kick top, as far as I remember, if you go to very large kicks, it actually goes to a stable state.
Depends on the parameter. So if you have a regular dynamics, then it oscillates. It shows quasi-periodic oscillations.
So which was later understood as a Anderson localization in the momentum space.
No, so this is not, it was not related to. So for example, here, so for example, if you take any linear entropy in this, it goes and saturates.
Yes. Yeah, I'm talking about the standard Shrikov.
No, I've not put any disorder here.
No, there is no disorder.
No, so no, I am not aware of
So
any.
standard kick top. Quantum
Yes, it saturates to some value,
yeah.
which is given by RMT in that subspace, random matrix theory in that subspace.
That can be explained as
That's a chaos. That's not localization.
there is a localization at strong drive. Standard
In a strong drive.
quantum kick top.
Mm-hmm.
And that is explained as localization in momentum space.
Momentum. Okay, momentum space. Yeah, that could be. Yeah.
So is it this? Does it have anything to do with it? Because it looks very different to me.
No, so my focus is in the disorder. Okay. It's a kick.
But here it's a fixed, it's like a spin. Maybe it's slightly
Yeah, so
different.
the dimension is different, right?
So your angular momentum is
It's a constant. It's a constant of motion. Yeah. Yeah.
The previous slide when you're showing what you called entropy, it just looks like 1 minus the purity.
Yes.
So, I mean, it's not like the entanglement.
It's not. It's just actually measuring the purity. Yeah, that's true. But you can also repeat this for some entanglement measures, and what we have seen is qualitatively similar. Yeah. Okay, so now we are introducing disorder in the interaction term, and yeah, so now if you take the disorder randomly from some normal distribution with 0 mean and variance W, then as expected, now there is no commutation of J square with the Hamiltonian. It's no longer a constant of motion, and it has lost its permutation symmetry, and instead of the without disorder model was restricted to the n+1 Hilbert space, but now it goes to the full Hilbert space. These are the things that I will also confirm numerically. So first let me see how the permutation symmetric basis looks like. For example, you can construct the symmetric subspace basis by, so there are these, if you have n qubits, you have n+1 basis, and these can be generated by, the first basis would be all up, the second basis would be 1 down, but these down can be anywhere in the chain. So a linear combination of 1 down anywhere in the chain, and similarly linear combination of 2 downs. So with this I prepare these n+1 permutationally symmetric bases, which are n+1 dimensions, and I'll be talking about various quantities. One of them is the overlap of the evolved state with this permutationally symmetric basis. And so let's see how this overlap evolves with time. So for example, and for different disorders. So I am going to start with some initial state, a general initial state with some theta and phi value, and as we know that if W is very small, then the overlap with the permutation symmetric subspace is very close to 1. That means it is still within the permutation symmetric subspace, it has not gone out. Now if I increase the disorder slowly, I will say that the magnitude of this overlap decreases, and for very large disorder it is very close to 0 after certain time. So we see that, as I said, that as you increase the system size, as you increase the disorder strength, the system is taken out of the permutation symmetric subspace, And this is a graph where I plot the saturation value of the overlap, long time saturation value of the overlap as a function of W for different k values. K is the one which determines the regular or chaotic phase in the disorder free limit or the classical phase space. And clearly when for small chaos parameter, what we see is that the overlap or the system comes out of the permutation symmetric subspace very slowly. So x axis is my disorder strength. On the other hand, when you are in the chaotic limit corresponding to the classical phase space, when you are in the chaotic limit, that is around k equal to 6, what we see is that even a disorder of small magnitude of disorder is able to take it out of the permutation symmetric subspace. Similarly, one can look at, as I said initially, for a disorder free Hamiltonian, J square is a constant which is n by 2 into n by 2 plus 1. But as I increase the disorder, J square decreases, and for very large disorder we find that the J square goes to some constant value, and that constant value is given by the random matrix theory. As we will discuss this in more details, but after crossing a certain disorder strength value, your various quantities saturates to one value, okay. And that value is given by the random matrix theory. This is the same J square as a function of W, and you see that this once you cross a certain limit, then there is this J square goes to some constant value, and that value actually is 3n by 4. So the other third quantity that I am focusing here is this von Neumann entropy, which is minus trace rho q log rho q, and here also same thing, that as you increase the disorder, the long time average of Sn by 2 saturates to some value, which again is given by the random matrix value, the value given by random matrix theory, which is the famous page value for large disorder. So again, this is the long time averaged von Neumann entropy plotted as a function of W. So as I said, so we see that after crossing certain disorder strength value, all the operators saturate to some common value, and that value is given by random matrix theory in 2 to the power n dimensions. So one can exactly show that for a J square if you take expectation value of J square in a random state, it gives you 3n by 4, and similarly this is the page value for full 2 to the power n dimensions corresponding to the von Neumann entropy. So this is for the values in the large disorder limit. On the other hand, in the zero disorder case, we know that J square has this n by 2 into n by 2 plus 1, that is the constant for the spin coherent state that I am starting with. J square is this constant, whereas this von Neumann entropy has a behavior which goes as logarithmically with the system size. So as you see, when you increase the disorder, this is the disorder free case. For example, J square scaling, as you increase the disorder, goes from some n square to n. Similarly, von Neumann entropy, as you increase the disorder, goes from log n to something like n.
So the threshold disorder strength, does that go down as you increase the system size, for example? Do you know how that depends on n?
Yeah, I'll just talk about that. My claim is that there is some phase transition, but let's see.
So, Uma, you have 10
Yeah,
minutes.
10 minutes.
Give
Oh,
me
okay. Okay, so this is just showing how J square scaling changes from n square to n, and similarly von Neumann entropy also log n to n, just to confirm that everything is correct. So now because there is some change in scaling, we think, so there is a possibility that it's a phase transition. So we thought of using some finite size scaling to monitor this change in, to figure out what kind of changes are happening, or is it a phase transition. And for what we find is that using this J square, what we find is that we get a good collapse at WC equal to 2.11 with some nu, and also there is an exponent zeta. So we, for these certain values of zeta, nu and WC, we see collapse. Now this is not sufficient to confirm, so we also did some variance, some further analysis of variance of J square, which again shows a peak around 2, which is what you get using the collapse also. Then we looked at all possible quantities, for example von Neumann entropy. This is all that I am doing is at k equal to 1. And if I look at von Neumann entropy, again there is a crossing point. If you do the finite size scaling, you have this crossing around 2, 1.93 in this case, and the exponent nu is within the error bar, same as the one that you get from J square. There is one more quantity that I use, the overlap that we discussed. So all the 3 quantities J square, von Neumann entropy and overlap shows similar behavior within the error bars. And so these WC was all done for one particular value, which is k equal to 1. You can also repeat this for other values of k, and for example we see that for k equal to 2 also there is this, we get some crossing and critical behavior. And we then tried with other initial conditions. So we did it with one particular initial theta phi. So if you change, so these are the different theta phi's that we took. Most of them except few, and the reason we know why they do not, but most of them show similar behavior and has critical exponent within the error bar. So these are some different initial conditions that we choose. This is just to show, this plot is just to show that for small w, if you look at the eigenvalues of the Floquet operator, so for small w it still has a Poisson-like, its w is 0.5. For k equal to 0.5, I think the WC was around 3. So for w small, much smaller than 3, we do have a Poisson statistics. On the other hand, for very large w, it goes to this COE ensemble-like dynamics. Now again, to summarize, we looked at various operators, changed the initial conditions, and these are the different values that we obtain for WC, for the correlation length exponent and the other third exponent. So nu and WC is, I think, reasonable enough to say that this is a phase transition. But still we can argue that it could be finite size effect because the system sizes that we have studied are not very large. So we thought of checking whether you can say that for there is a possibility of, say for example, J square going as n square in the infinite limit. If I can show that, which means that there will be a non-zero WC. So now what we did is, we did this analytical calculations for p equal to 0 limit, which means there is no kicking. So I have this disordered all-to-all interacting spins, and I want to find out the expectation value of J square in this all-to-all interacting for the same spin coherent state. We do the disorder averaging everything, and what we get at the end is a term like this, which has this first term is this 3n by 4, and the second term, as you see, has this this second term of the second term. You see that that's the only term where time comes, and it exponentially decays. So it goes to, so this term goes to 0. So in the large time limit, what you have is 3n by 4 plus some n square term into something which depends on my initial state theta phi. Okay, so now but you see that if you have for a generic theta phi, we will always see that J square goes as n square. There are certain theta phi's, for example, if phi is pi by 2, then you have J square going as n, but for a general theta phi, J square goes as n square. Now how does it help us to argue that there will be a non-zero WC? So this is just to compare my analytics and numeric. So what we see is that without kicks, that's the calculation that we did. J square saturates to some disorder independent values. It depends on initial state, but it is independent of the disorder strength. And without kick, it just depends on theta phi and scales as n square for a general state. Now, now let me go to the point where I want to give some hand waving argument that there is a possibility of non-zero WC, and that is that if you so this is my Floquet operator, which I am going to decompose this as u epsilon and u naught. U naught is my Floquet operator of the disorder free Hamiltonian, and I just take out this epsilon term. Now, if your disorder is very small, then I can write this is the actual Floquet operator. Now, if the Floquet operator after nth step that I want to apply on the initial state, if in the limit of very small w, I can decompose it as just u epsilon to the power n and u naught to the power n. Now, the state at nth time step would be this operator operating on psi naught. If you look at it, see the psi naught is a spin coherent state on which u naught is operating. U naught is a disorder free unitary operator. It will take a spin coherent state and take it within the permutation symmetric subspace, because it is a disorder free Hamiltonian. So, this term will always be within the permutation symmetric subspace. Now, we have to apply u epsilon to the power n to a state which is within the permutation symmetric subspace. And we have already seen that for a generic theta phi, if this p equal to 0, that u epsilon is like my p equal to 0 Hamiltonian analytics that we did, for a generic theta phi, it will always scale as n square. Okay. So, therefore, our claim is psi n will continue to have n square scaling for small epsilon even for large n, and hence there is we feel that there will be a non-zero WC even in the large n, although this analysis only for small epsilon.
Also the approximation that u naught and u epsilon you're commuting, that only holds for up to some large little n, right?
Correct. Time you are saying, correct. Then the errors will that's true. Very small epsilon, yes, that's true.
Sorry, so for topology I missed your J square conservation, so that's fine. So the second thing is, won't you expect that the epsilon will be a singular perturbation because it breaks the symmetry?
Epsilon is a perturbation.
Singular perturbation. Means just you put infinitesimal of it and then
it breaks the permutation symmetry. Yes.
So
even small amount of this.
Really matter that 0 and 0.
Yeah. No. So, but we can. You're saying. So that's our claim that there will be a small value of disorder below which the system will be predominantly within permutation symmetric subspace.
I see.
And scalings would be just like permutation.
I see.
N square. Yeah. That's the end of the talk. Yeah.
Are you done?
Yeah, I'm done. This is the last slide.
Okay. We can have 2 or 3 quick questions.
Yes.
When you have a very small disorder, then I can think this problem as a completely permutation symmetric. So you are getting n plus 1 I squared states, whereas j and jz is plus j. And this is like the greatest case where you have no magnon, one magnon, and so on, one half spin flip. So if I start from such a state,
With what kind of state?
let's say j and jz is j. So
Yeah, that's Jz is J. That's the n by 2. Yeah, correct. So that will be my theta 0.
correct. So if I start from that state, then will it give a large cutoff, this large critical WC?
No, we still find it to be WC. We check the 0 state and we still find it to be close to 2. Yeah.
Any other question?
So right now you're doing a kicking model, but if I had a static Hamiltonian with both parts, like xx and y, So then it's like a disordered all-to-all transverse free Ising mode.
Correct, correct, correct.
So do we know if that this sort of transition happens in that static Hamiltonian, just as a function of WC? Is there any transition?
I'm not aware of, yeah, unkicked and a transition, yeah. I don't think so, yeah. Yeah.
So yeah, in presence of disorder, you are basically kicking a sharing Kirkpatrick spin glass, right?
Yes, 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 yes.
So the question is whether it is in this setting it's a quantum spin glass transition or something like that which you are seeing. If you do this effective Hamiltonian thing, would you come up with a quantum spin glass as an effective Hamiltonian and it goes through a glass transition?
I don't know, have to see, yeah.
It looks like first few terms, if you just analyze, you will get something of this effect.
I
You
see.
might get.
I see, I see.
And it's
People
already a
might
glass
understand.
to start with.
Sorry?
It's already a glass to start with.
That's what I'm saying, but you are kicking it.
Kicking,
So you
yeah.
just might have an effective Hamiltonian H effective because it's a periodic thing. You can always write a proper Hamiltonian, so it still can be glassy. And if you don't believe that eventually everything heats up, then probably you can have a glass transition.
Okay, if there's no more question, let's thank Uma for
Thank
the
you.
talk.